Good morning, everyone. So recall that in the last class we have seen how to solve a homogeneous linear recurrence relation by assuming an is equal to alpha raised to the power n. In today's class we will see how to solve non-homogeneous linear recurrence relation. To solve non-homogeneous linear recurrence relation, we will use the method of undetermined coefficient, which is same as we use in the differential equation. So for example, if I have to find a particular solution, now what does it mean by particular solution? It is a function of n which is satisfying the non-homogeneous recurrence relation. Non-homogeneous, yes. So now if you see it, then you first try to see the recurrence relation as in this form, because then you can realize that left hand side is the homogeneous part, right hand side is the non-homogeneous part. Now irrespective of the left hand side, you can see that the right hand side is a polynomial of degree 1. It means that a polynomial of degree 1 is going to satisfy this recurrence relation. So based on the right hand side, we choose the nature of the particular solution. It means that my particular solution would be, if I denote it by P of n, would be something like B0 plus B1n, where I need to find B0 and B1, and I assume it is a particular solution, it must satisfy the recurrence relation. So if I put it back, then an, so Pn, if it does not create any confusion, then Pn means an even, which means the solution of the recurrence relation. So B0 plus B1n minus B0 plus B1n minus 1 minus B0 plus B1n minus 2 is equal to 2n. Yes. Now if you simplify it, then B0 minus B0 would cancel out. So B11 and this B1n would cancel out. Minus minus, so becomes B1, then minus B0 plus B1n minus 2B1 is equal to 2n, which means that it becomes, this becomes plus 2B1, sorry, because minus minus would become plus. So 3B1 minus B0 plus B1n is equal to 2n. Yes, we can simply see, okay, there are some more small mistakes also there. This B1n is also minus, so this is also minus. If you compare the coefficient, then the coefficient of n on the left hand side is minus B1, on the right hand side it's 2. That gives you B1 is equal to minus 2. And that also gives you 3B1 minus B0 is equal to 0. It means your B0 is 3B1, which is minus 6. It means P of n is equal to B0 minus 6 minus 2n. So this is the particular solution of the non-homogeneous linear recurrence relation. Yes. Now let's say I have to find the general solution of this non-linear homogeneous recurrence relation. So to find the general solution, the approach would be to find the general solution of the homogeneous part. It means I have to find the general solution of an minus 1 minus an minus 2 is equal to 0, and then I add particular solution of non-homogeneous part is equal to 2n. That gives me the general solution of the non-homogeneous linear recurrence relation. So as I told you, it is similar to the method of the undetermined coefficient only. We will use the logic, we are not going to the detail. But if you recall the method of undetermined coefficient, things would be clear to you. And of course you see the coming example. Now it says find a solution. It is not saying find a particular solution. Particular solution is restricted to a solution of the non-homogeneous. When you say solution, it means you need to find the general solution of given recurrence relation satisfying the initial conditions. Yes. So as I told you, for the general solution I need the homogeneous part. So homogeneous part is an minus 1 minus 2 an minus 2 is equal to 0. Yes, this is the homogeneous. So I need the general solution of homogeneous plus particular solution of non-homogeneous, which is an minus 1 minus 2 an minus 2 is equal to minus 4. General solution we have already discussed in the last lecture. So for the general solution, take an is equal to alpha raised to the power n, that gives you alpha square minus alpha minus 2 is equal to 0. That gives you alpha is equal to minus 1 and 2. It means the general solution of homogeneous recurrence relation is, you can define any constant. So for example, c1 minus 1 raised to the power n plus c2 2 raised to the power n. Now the particular solution would look like, it is a polynomial of degree 0, so some constant b. Now put it back into the non-homogeneous recurrence relation, it becomes b minus 2b is equal to minus 4. That gives you b is equal to 2. So it means general solution of given recurrence relation is c1 minus 1 raised to the power n plus c2 2 raised to the power n plus 2. Yes. Now I have given the initial conditions. So a naught is equal to 0, a naught is equal to 6 implies this is the general solution. So an is equal to this. So a naught means n is equal to 0. So c1 plus c2 plus 2 implies c1 plus c2 is equal to 4. Next is a1 is equal to 7, implies 7 is equal to, n is 1. So minus c1 plus 2c2 plus 2 implies minus c1 plus 2c2 is equal to 5. Now solving this, you add them, that gives you 3c2 is equal to 9. So c2 is equal to 3 and c1 is equal to 1. It means that the required solution is an is equal to c1 is 1, so minus 1 raised to the power n, c2 is 3 plus 3 2 raised to the power n plus 2. That gives me the required answer. Now the next question is, we don't have the space, so I may have to move to the next slide for the space. Find a particular solution of the linear recurrence relation an is equal to an minus 1 plus 3 an minus 2 plus an minus 3 plus 3 raised to the power n. Now I need a particular solution. It means I just need to see the non-homogeneous part. It is of the form 3 raised to the power n. It means that the solution must be of the form some constant multiplied by 3 raised to the power n. Yes. So let me move to the next slide for the space. We will solve it later. So I am writing the recurrence relation an minus 1 minus 3 an minus 2 minus an minus 3 is 3 raised to the power n. So let Pn is b times 3 raised to the power n. If you substitute the values, b 3 raised to the power n minus b 3 raised to the power n minus 1 minus 3b 3 raised to the power n minus 2 minus b 3 raised to the power n minus 3 is 3 raised to the power n. Now you simply need to find the value of b. So b comes out to be 27 by 8. Try it by yourself. That gives you Pn is equal to 27 by 8, 3 raised to the power. Now next question is general solution of an is equal to 2an minus 1 plus 2 raised to the power n. So let me write down the recurrence relation here. An is equal to 2an minus 1 plus 2 raised to the power n. Now I need a general solution. It means the homogeneous part is an is equal to 2an minus 1. That gives you alpha minus 2 is equal to 0. Alpha is equal to 2. An is equal to some constant 2 raised to the power n. Now if you take the particular solution as some constant multiple of 2 raised to the power n, then you can see that this p of n would be same as it is a part of the homogeneous recurrence relation. So if the root of the characteristic equation for the homogeneous part is same as, so for example the root is 3 and in the non-homogeneous part you have 3 raised to the power n, then your p of n would become the part of the general solution of the homogeneous part. But we need it independent, otherwise particular solution would not be in the picture. So it is the same concept again, the differential equation. This p of n should be linearly independent, which means it should not be the constant multiple of any of the solutions of homogeneous. So let's say you are getting 3 solutions, 3 raised to the power n, 5 raised to the power n, 7 raised to the power n. So your p of n should not be a constant multiple of 3 raised to the power n, 5 raised to the power n or 7 raised to the power n. So it means that instead of taking it as this, I should take Pn as Bn2 raised to the power n. If there have been equal roots of the characteristic equation, for example 2 comma 2, then the characteristic equation gives us the solution as 2 raised to the power n, n2 raised to the power n, and in that case you take Pn as n square 2 raised to the power n, and so on. So now I got Pn, so I have to substitute it back into the given equation. So the given equation is Bn2 raised to the power n minus 2 times Bn minus 1 2 raised to the power n minus 1 is equal to 2 raised to the power n. Again if you solve it, then b comes out to be 1, and that gives you the general solution. An is c2 raised to the power n plus n2 raised to the power n. Now comes the last question, which says that solve the differential recurrence relation. An is equal to 3n minus 1 minus, so we need to solve to find its general solution, and also we need to find the solution when a1 is equal to 8. So for the general solution, first I have to solve the homogeneous part. So an is equal to 3an minus 1. That gives me alpha is equal to 3. Alpha is equal to 3 implies an is equal to c 3 raised to the power n. Now if you see the non-homogeneous part, then it is an minus 3 an minus 1 is equal to minus 4n plus 3.2 raised to the power n. So instead of the non-homogeneous part is made up of two functions now. It is not only g of n, it is g1 of n, g2 of n. So to find the particular solution, I consider one at a time. So for example, I need to find particular solution when an minus 3 an minus 1 is equal to minus 4n and an minus 3 an minus 1 is equal to 3.2 raised to the power n. In this case my p1n is b0 plus p1n. In this case my p2n is b times 2 raised to the power n. Now I substitute the values. So b0 plus b1n minus 3 b0 plus b1n minus 1 is equal to minus 4n, and in this side b2 raised to the power n minus 3 b2 raised to the power n minus 1 is 3 2 raised to the power n. Yes, if you solve it further, then it gives you b0 is equal to 3 and b1 is equal to 2, which means my p1n is 3 plus 2n. And here if you solve it, then capital B comes out to be minus 6. It means p2n is minus 6 2 raised to the power n. It means your general solution an is c times 3 raised to the power n plus 3 plus 2n minus 6 dot 2 raised to the power n. Now for a1 is equal to 8, you just substitute n is equal to 1 and that gives you c is equal to 5. It means the required solution is 5 multiplied by 3 raised to the power n plus 3 plus 2n minus 6 dot 2 raised to the power n. So in the next class we will discuss the last section where we are going to see how to solve the recurrence relation using generating function. Thank you.